Stephen Hawking's black hole theory. In this video we will talk about Hawking radiation. In the late 1960s, Penrose collaborated with his Cambridge friend and colleague, Stephen Hawking, in more investigations into the subject. They applied a new, complex mathematical model derived from Einstein's theory of general relativity, which led, in 1970, to Hawking's proof of the first of several singularity theorems. Such theorems provided a set of sufficient conditions for the existence of a gravitational singularity in space-time, and showed that, far from being mathematical curiosities which appear only in special cases, singularities are actually a fairly generic feature of general relativity. Although it may seem a very complex, peculiar and perhaps counterintuitive object, a black hole can essentially be described by just three quantities: how much mass went into it, how fast it is spinning, its angular momentum, and its electrical charge. This came to be known as the no-hair theorem, after John Wheeler's comment that black holes have no hair, by which he meant that any other information about the matter which formed a black hole, for which hair is a metaphor, remains permanently inaccessible to external observers within its event horizon, and is all but irrelevant. Brandon Carter and Stephen Hawking proved the no-hair theorem mathematically in the early 1970s, showing that the size and shape of a rotating black hole would depend only on its mass and rate of rotation, and not on the nature of the body that collapsed to form it. They also proposed four laws of black hole mechanics, analogous to the laws of thermodynamics, by relating mass to energy, area to entropy, and surface gravity to temperature. In 1974, Hawking shocked the physics world by showing that black holes should in fact thermally create and emit subatomic particles, known today as Hawking radiation, until they exhaust their energy and evaporate completely. According to this theory, black holes are not completely black, and neither do they last forever. Hawking showed how the strong gravitational field around a black hole can affect the production of matching pairs of particles and antiparticles, as is happening all the time in apparently empty space according to quantum theory. If the particles are created just outside the event horizon of a black hole, then it is possible that the positive member of the pair, say, an electron, may escape, observed as thermal radiation emitting from the black hole, while the negative particle, say, a positron, with its negative energy and negative mass, may fall back into the black hole, and in this way the black hole would gradually lose mass. This was perhaps one of the first ever examples of a theory which synthesized, at least to some extent, quantum mechanics and general relativity. A corollary of this, though, is the so-called information paradox or Hawking paradox, whereby physical information, which roughly means the distinct identity and properties of particles going into a black hole, appears to be completely lost to the universe, in contravention of the accepted laws of physics, sometimes referred to as the law of conservation of information. Hawking vigorously defended this paradox against the arguments of Leonard Susskind and others for almost 30 years, until he famously retracted his claim in 2004, effectively conceding defeat to Susskind in what had become known as the Black Hole War. Hawking's latest line of reasoning is that the information is in fact conserved, although perhaps not in our observable universe but in other parallel universes in the multiverse as a whole. Unfortunately, Susskind's proposed solution is even more difficult, and almost impossible to envisage or explain in an understandable way. He suggests that, as an object falls into a black hole, a copy of the information that makes it up is sort of scrambled and smeared in 2 dimensions around the edge of the black hole. Furthermore, Susskind believes that a similar process occurs in the universe as a whole, which raises the rather alarming idea that what we think of as three-dimensional reality is in fact something like a holographic representation of a real reality, which is actually contained in 2 dimensions around the edge of the universe. It is also theoretically possible that primordial or mini black holes could have been created in the conditions during the early moments after the Big Bang, possibly in huge numbers. No such many black holes have ever been observed, however. Indeed, they would be extremely difficult to spot, and they remain largely speculative. It is anyway likely that all but the largest of them would have already evaporated by now as they leak away Hawking radiation. According to Hawking's theory, the amount of mass lost is greater for small black holes, and so quantum-sized black holes would evaporate over very short time scales. But it is hoped that such many black holes might be experimentally recreated in the extreme conditions of the Large Hadron Collider at CERN, which, among other things, would lend much-needed credence to some of the current theoretical predictions of superstring theory regarding gravity.